Good morning, everybody. We will start now with day number 2. I hope you have had a good afternoon yesterday and some rest. Let me start to repeat something about what we have discussed as a last point, which was laser Doppler velocimetry, just to remind you what this technique actually was built on, and to see then subsequently the differences to particle image velocimetry. So first of all, this is a particle-based method where we have to seed suitable seeding particles into the flow. And we have discussed that depending on whether you're only interested in isothermal flows, where oil droplets, aerosols are clear beneficial or much better than chemically inert particles that are solid particles for combustion applications. So the big problem here, or the big issue typically, is to select good particles and to bring them into the flow that you have a constant seeding density. Then in LDV, based on a CW laser, you create here, by crossing them, an interference pattern. If I magnify this here, an interference pattern such that you have a certain distance, a known distance between these stripes, which is dependent on the angle between these two laser beams. And then you might have here your particle crossing this interference pattern, and what you're actually measuring is the velocity component perpendicular to this pattern. And that is then, over time, a signal, a so-called burst, where the intensity over time varies according to these interference stripes, and so on. And what you make is here an estimation of the transit time the particle needs to cross over from one interference stripe to the next. And with that, you get this one velocity component, which is, if this is delta x over here, simply the estimation of delta x over delta t. We have seen that with that approach, you would not be able to distinguish whether the particle comes from the top or the bottom. And that's why you have here not exactly the same frequencies, but if you have here, let's say, maybe to take f, the laser frequency, the other one does have a slightly different frequency, which is shifted by a Bragg cell that we have seen is made of a acousto-optic modulator, where you change the frequency by the interaction of the light wave with acoustic wave. And with that approach, you're able to measure at single locations the probe volume. The probe volume is extended independence of this crossing area over here, and is in the, let's say, range of 0.5 millimeter at best up to, let's say, something like 1.5 millimeter. So the smaller the crossing angle, the larger the length of this volume. And perpendicular to that, you have a diameter in the order of, let's say, 50 as well to 150 microns. That as well depends on your focal length. It depends on the beam diameter at the lens as the most important parameters, because the wavelength typically is given by the laser you're using. Okay, so this was the basic principle. It's a robust technique that allows you to deduce single point statistics, mean values, variances, and as well, if you do correlation measurements in time, for example, to come up with length scales like the integral length scale, the temporal length scale, which can be then deduced or transformed to a power spectral density. And if you have a higher experimental effort, you can do LDV with 2 setups and then measure the correlation between adjacent points. And then deduce integral length scales, and as well, in principle as well, you can deduce from that by Fourier transform a power spectral density in the wave number regime. Okay, it is limited to a small area, a point, and that's why it is taking a lot of time if you have a flame, because you have pointwise to go through the field. For that reason, particle image velocimetry is a technique that became, something like a replacement of laser Doppler velocimetry, because it's much faster. So the principal idea is shown over here. You're not using a CW laser anymore. What you're using is a pulsed laser, and you need a laser that emits at least 2 pulses where the temporal distance, delta t, can be adjusted. So these 2 pulses nowadays are typically extracted from neodymium lasers and operated at 532 nanometers in the visible, because there our CCD and CMOS cameras are rather sensitive. Then, out of this beam, you create a light sheet. A light sheet with some transforming optics, which are not shown here, that can be simply something like a 1 cylindrical lens. It can be as well combined with a telescope, because you might be interested in having a larger cross-sectional area. Okay, that is something that really needs to be adapted to your experiment. Then you have here a light sheet with a typical thickness in the order of, let's say, 200 microns up to a millimeter, maybe 1.5 millimeter. The reason is you cannot afford to make this light sheet very thin, because the idea of PIV is that you illuminate particles at these 2 instants with these 2 pulses and monitor the Mies scattering perpendicular to the light sheet on a camera, a CCD or a CMOS camera. And you're relying on the fact that at least most of the particles during the exposure number 1 are in the light sheet and stay in the light sheet. If you would have a very, very thin light sheet, you would have, by turbulent motion, by swirl, for example, by out-of-plane motion, more generally, you would lose particles out of that projection plane. And that is something, of course, you have to avoid. And that comes, this is a certain limitation in 2-component PIV, that your resolution as well in depth is limited by this out-of-plane motions. Yes?
What was the thickness range again?
Typically, it depends, of course, on your flow, between 200 microns and 1.5 millimeters. If you go for a swirling flow, for example, and your swirl direction is an out-of-plane, then you need to make it thicker, but independent as well of the delta t. Of course, if you choose a very short delta t, then you can afford to have as well a thinner light sheet. But that is as well something that needs to be adapted to the velocity range you're after. Okay, so let's assume that you now have 2 exposures with which you have measured the instantaneous position of particles. Yeah, this is shown over here, image from pulse number 1 and image from pulse number 2. What you do then is you subdivide this area into so-called interrogation volumes, which are these small squares over here. And here in the magnified view is a sketch where you now see as these dots the instantaneous locations of the particles. So the idea of PIV is now that you just look for the most probable shift of this particle pattern between these 2 exposures. Let's say you have had 3 particles in the first image, and then you're looking in the second image, where have they moved to? And you're looking for this most probable shift that these 2 patterns are matching best possible. And this is done by a cross correlation, where we see later on how this is done mathematically, and allows you now to make a guess of the velocity within such an interrogation volume. So this is something that defines your spatial resolution, and you're looking here based on typically the advice is around 10 particles in such an interrogation volume. You're looking for the most probable shift in this area. Okay? A very different technique compared to laser Doppler velocimetry. So once again, you have seen that yesterday. If you have a raw image like that for the first exposure, then you have the second exposure, and I go back and forth, and you can see by your eye, by your brain, which is a very good cross-correlator, where the particles might have moved to. And so that is what the algorithm is doing based on an estimation on a certain number of particles. And as I said, this number of particles, the advice is to have at least something like 10 particles in this interrogation volume, from which you then can deduce, in this case, two components of this velocity field in the intersection plane of the laser. Okay, so that is shown here. Once again, here is your field of view. Then you have a imaging system, a lens, that brings now this particle image here onto your CCD, where you have the discretization and as well the recording. It's very important in PIV that you very thoroughly do the calibration. So different than to LDV, you need a calibration, and the calibration means you have to bring the physical scale, millimeters, here onto the CCD or CMOS array, which is made out of pixels. And you have a certain magnification, and that needs to be accounted for by calibration plates. For example, here for stereo PIV, for two-component PIV, it would be just a flat target where you have dots, clear marks with a known distance to each other, such that you can transform from millimeters to pixels. And that is a very, very important thing that needs to be accounted for and is, as I said, different to LDV, a calibration step. Yes, please.
How do you do that in a combustion chamber?
The question is, how do you do this in a combustion chamber? I have to repeat that for the recording. It depends now on what kind of chamber you're speaking of. Let's take an engine, for example. Well, you have to lift off your cylinder head, you place it with a good arrangement at the location where later on your laser beam will be. You align that at the location where the laser beam is, and then you do the recording as you would in the real experiment. You do not account for any changes of the index of refraction. Yeah? That is something, if you have a severe change over there, then you're in trouble. Okay, but if, especially in engines where you have a curved liner, you have distortions. And these distortions need to be accounted for, obviously. Okay? All right. Nowadays, people are using, when they're using CCD cameras, so-called interline transfer CCD cameras, where you are able to make two exposures, which are shown over here, T and T prime, where the particles have moved. Of course, if you have a very low velocity, you need to have a longer time interval between these two exposures, because you really want to see that the particles have moved. You have only a discretization which is limited, and if the motion is or the displacement is too small, you will be not very precise. And so another advice is that in PIV, within one interrogation volume, the displacement should be in the order of 25% of the length of this interrogation volume. And that brings you already to the point when you have in your field of view different velocities. Maybe you have a backward-facing step, high velocities in some location, recirculation, and negative velocities as well, including maybe regions where you have more or less stagnant flows. There, PIV suffers from the dynamic range. So this is a critical issue. Okay, once you have then performed these two images or taken these two images, then this camera takes a certain or needs a certain time for readout, the CCD camera at least, and then you repeat that. So in principle, the principle is very nice, but in practice, there are a lot of, let's say, experience needed to come up then with a reasonable choice of the parameters of delta T, thickness, and so on. That needs to be as well changed in the experiments until you find an optimum. It's kind of experience and empirical. About the cross-correlation with some more words. Here we see an example of the two exposures at T and T plus delta T. Superimposed, you see the interrogation volumes. Two of them at these two times are extracted over here. And as I already said, the size of these volumes determine your spatial resolution. So typically you have here in the order of, let's say, 32 by 32 pixels is very often used, or 16 by 16 pixels. And it depends now on your magnification, what is that corresponding to in the spatial domain. The cross correlation itself is nothing else as searching for the most probable displacement where you find the best match of your particle pattern. Okay, how is that done? Starting from a certain pixel over here, from your first exposure, you shift now your mask with which you do the correlation to other areas. Here are shown 5 of them. And then what you do, the corresponding pixels are multiplied by their intensities. And then you do this pixel-wise and sum them up, such that you end up with a correlation map. And the correlation map might have some shifts where you have a very high cross-correlation value, and other locations maybe where you do not have a very high cross-correlation value. And then you just go on and say the most probable shift is that where the value of this cross-correlation operation is at maximum. That's the typical procedure. Please ask if that's not clear. In practice, because of computational time, it is done after a Fourier transform. So it's not done in the physical space, but it's done after transformation in the wave number space. Because the only reason is that the cross correlation in the Fourier space is simply a multiplication of these Fourier transformed images. And that means that you have here now in wave number space your cross correlation plane. Of course, that is not the end. You have to go back to this physical space, and what you do is an inverse Fourier transform where you go back into the spatial domain, where you now see here the correlation map of these 2 interrogation volumes, where you see that the correlation volume, the correlation peak seems to be here. So the most probable shift is in this direction. So here, by this example, it was only in x direction. Of course, if the correlation peak would be somewhere here, it would be then the shift in this direction. And then based on that value, you have an estimation of the velocity average in that interrogation volume. You have to be careful about the resolution. If you would restrict yourself only to the discretization given by these pixels, you would have so-called pixel locking. So the idea is that you now, to have a sub-pixel resolution, you fit something like a Gaussian function over this correlation peak, and thereby you're able to reduce the discretization step size to something which is maybe a tenth of a pixel or so. And that is crucial because otherwise the dynamic range would be very, very limited.
This is the same thing as a windowing function.
This is the same effect as windowing. That is correct. And then you repeat these operations for the whole field of view. And then you get, for this realization, the velocity field, and you typically end up as well with a few spurious vectors. So first of all, the number of these vectors that looks strange should be not really large. Obviously, these vectors over here, they cannot be correct. That is, of course, our knowledge based on continuity and fluid mechanics that is physically not realizable. And then the idea is if the number of these spurious vectors is acceptable low, let's say 5% or so, you use the information from the neighborhood to smooth them out. In a thorough description in a paper, you should find some statements about the percentage of these erroneous vectors. If this is not given and the vector field looks very nicely, be careful. Yeah. So ideally then you go, if you do the experiment on your own and you find that here maybe 30–40% are looking strange and not really physically consistent, then you have to do something on your parameter settings. It could be due to the particle density very often. So count the number of particles in your probe volume. It could be that you're losing many of the particles between the two shots, so you should make the delta T smaller or the light sheet thicker. These are, as I said, different things that needs to be controlled by the experimentalist, and there is not the best way, because you have different, let's say, possibilities to overcome a bad image. Okay. And this brings me back to what I've shown yesterday already, where we have here an optical accessible engine, which is seeded with, I think this was oil droplets in that case, where we're interested in cyclic variations due to injections. And this image you see here is after post-processing and correcting the spurious vectors, and there might have been in the order of 5% of them. And this is done with the CMOS camera, which is a different camera principle, where you not only can do 2 exposures successively, but depending on the onboard capacity, you might be able to take, I don't know, 10,000 images. And that allows you then to come up with this, let's say, insight that is not accessible by LDV. And you can see structures with a certain resolution that provides you an insight that can be very helpful for understanding what's going on. Okay, I'll finish that here. From these data, you can deduce, again, single point statistics, meaning mean velocities, velocity fluctuations, and of course from that as well the Reynolds stress components. If you have 2 components measured only, then of course you can deduce only one of these off-diagonal Reynolds stresses. More important maybe is that you can deduce as well derivatives of the velocity field, which are of course limited by the spatial resolution you have. But out of these derivatives, you're able then, for example, to calculate vorticity, the out-of-plane vorticity in case of 2-component PIV, meaning that is a value for the angular momentum. Or the dilatation. If you have, for example, a flow that is opening like that, then this opening of the streamlines can be linked to this dilatation that is defined as here under transparency. I would say, at least for spatial correlation measurements, PIV is less suited. And that is due to the fact that the spatial resolution typically is limited to something, in conventional PIV at least, to something like 200 microns, 500 microns, or in that order of magnitude. Very often as well you find PIVs which are less resolved. And that's why a spatial correlation is not as good as to be deduced as from LDV, with 2 LDV setups where you can have these probe volumes very close to each other. So that is really something which is not as good. In the temporal domain, it might be better. With the advent of high-speed PIV, you can, for a single location, then trace that velocity in time. And so I would say temporal correlations are okay, although the resolution you can achieve is as well worse than that with laser Doppler velocimetry. Okay. So this is the principle and the most, let's say, fundamental parameters you can deduce from this 2-component PIV. Of course, you can do, okay, this is questions.
Can this technique be used for measuring the flow field in a plane that's already laden with particles, for example, silica particles in optical fiber?
Yeah. So the question is whether this technique can be used in flames where you already have, by nature, particles included. Yes, of course, you can. You will measure the particle velocities, as I said. If you have particles that follow the flow with no slip or very small slip, it's actually the gas or fluid velocity. If you have large particles, let's say go to coal combustion, where you might have particles of 100 microns or so, which have a large slip, then you're measuring the particle velocity of your 2-phase flow. And that can be as well, of course, of interest that you're interested in, not in the fluid or gas velocities, but in the particle velocities. Yeah. Yes, please.
The spurious vectors that you mentioned, they are related with the preconditions that you have in the experiments. I mean, for example, reflections or bad alignment between the laser sheet and the camera.
Yeah. So the question was where these spurious vectors origin from. So of course you have different possibilities. So maybe you have regions in the flow where you have a larger out of plane velocity. In that area, then you will lose the particles, and the correlation will give you some, let's say, maximum, but it might be wrong because it's just arbitrary, depending on which particles come in the next shot, which have been moved in out of plane direction. It can be reflections, of course, although reflections can be handled. You just take then one exposure without the particles and store that, and then you subtract it from each of the images. You correct for the background. That means that your reflections should not saturate your camera. It's very important. If you have saturation, then this doesn't work anymore. So there are more than one reason why it could be. But these are two examples, yes. Okay. Yes. Oh, here's another question.
What are the restrictions when trying to go higher resolution than the 200 microns you quoted?
So what are the restrictions for higher resolution? You have to have something like, as I said, let's say 10 particles in your interrogation volume. If it goes smaller and smaller, you have to seed denser and denser. And that means at some stage, of course, you might change your flow. Take, for example, a flow, or let's take a flame, for example, where you're interested in extinction. And then, if you have a high particle load, the extinction limits can be shifted, which means, that your method is really intrusive. And that is a limitation. Another limitation might come from the fact that yeah, well, of course, optically you can do better than that. But if you would focus your laser sheet thinner and thinner, because it's not only the in-plane resolution, but as well the out-of-plane resolution, you would have to adapt your delta T. Yeah, if it's thinner and thinner, the probability to lose the particles from one to the next exposure is increasing. And that means the delta T has to be reduced. And that means that the in-plane displacement is getting smaller and smaller. And then you will be less accurate in your estimation of that displacement because of the discretization, which is as well limited. Okay? Okay.
Talk about adaptive cross-correlation. Is that just using the neighboring interrogation area to estimate something for the interrogation area that we don't have enough information for?
I'm not sure whether I got the question correctly. You're talking about an... Yes. So the adaptive cross-correlation. By that, you're referring, for example, to something where you, depending on your flow, you distort, for example, your interrogation shape, for example, things like that. That is nowadays implemented in codes to make your estimation or improve your estimation. And yeah, I would say is really important for a better estimation. Although the problem I would say here is that when I refer back to what we have done, I think we gave up in 2008 to develop our own PIV code. Because the commercialized codes, which were developed with a lot of manpower, have used all these additional tricks from fluid mechanics. But the problem really here is that you do not really get access to the source code. So you do not really know what they are doing in detail. So all they offer to you is benchmarking against the PIV challenges, which are typical examples where the codes are checked against. But that's why I cannot really answer your question about this adaptivity. What they, for example, in the different codes from TSI or Duntech or LaVision and the different companies are actually doing. But the idea is that, of course, that you not restrict yourself only, let's say, to certain shapes of the interrogation volume, but you distort them depending on the convection and flow velocities. Yeah. Okay. You can do more than 2 components. You can go for 3 components, as discussed yesterday or briefly, by looking with different perspectives, or you extend that even more and go for volumetric imaging, where you then have here not only a sheet of, let's say, 0.5 millimeter, but of a couple of millimeters. Restricted by the fact that you still need to identify these single particles without, let's say, having so-called ghost particles and particles in the line which are obstructing the view on the particles in this volume over here. So typically you need more pulse energy than for 2-component PIV. And the field of view might be different in plane and out of plane. As I said, it's restricted to a couple of millimeters. And here you see, again, the example from the engine. Very important is not only that you have a laser with a bit more energy and of course adapted optics to illuminate a volume. You need then, the advice is something like 4 to 8 cameras. And then these cameras should be ideally identical. They should be equipped with the same lenses, such that you have the same transfer function, the same imaging capabilities. And you should choose as well an appropriate angle. In the literature you find that here 30 degrees seems to be a good choice. And then you end up with something like that. So now it's even more post-processing. And there's not only one single way to do it. It is, as always in image post-processing, something like empirical trial and error. And you have to check in the end the results on their consistency by inspecting them, and maybe as well have canonical flows to check against. But it's as well depending on the seeding density. So it's not easy, and it's maybe not fully trustable. So here, in this example, image pre-processing has been done by subtracting a sliding average. And thereby you already see, thereby you get a better contrast. Then the intensities have been normalized, and they have been smoothed by a filter. And then again, to come back with better contrast, the particles again have been sharpened. Then you have, you need a reconstruction where the particles as well in the volume are located. And this is done here with this code with a MART reconstruction, where you have now a reasonable estimate for the first exposure where the particles actually are. And then you do that with the second image or the second volume as well. And you do then a volume correlation. You try not only to do that now in the interrogation volume which is plane, but that's now something like a box. And from that on, you receive something like here, an image shown over here for a certain crank angle degree. Very difficult to see what here is this 4 or 8 millimeters, and this is the in-plane field with vectors in the order of, let's say, 0.4 millimeter resolution in this case, depending on the size or the thickness of this volume. And that can be helpful if you want to see structures volumetrically, and it can be helpful if you want to get derivatives in all directions. Yeah? Because with the 2-component PIV, you were able to deduce the derivatives only in plane. Now you have them in all directions. And that can be useful to better understand that flow. But it's quite a large effort. And the post-processing is even more critical, I would say. And as well, what you do here is an outlier detection, because you refer to the neighborhood, what actually the surrounding is, and you try to remove those vectors which seem to be not physical. And as well, here we have performed some Gauss smoothing such that the fields are looking nicer. But of course, this is a kind of low-pass filter reducing your spatial resolution such that it's not so easy to really say what is your spatial resolution in the end. Yes?
So how do you focus the camera? Do you focus it to a plane? Do you open the depth of field to capture it?
Yes. So the question was, how do you focus your cameras? Of course, the depth of field is an issue. So what you do is you have a so-called Scheimpflug adapters, such that the depth of field in a certain range is extended, and you increase your aperture, in the sense you go from f4 maybe to f16. So you close that and thereby increase the depth of field from something like, I don't know, maybe a millimeter to something like 10 millimeters. And that means you lose a lot of light, and that's why you need much higher pulse energies. Yeah, that is something you have to compensate. And in two-component PRV, for that field of view, maybe a millijoule in an engine would be okay. And if you do tomographic PRV, you might need tenths of millijoule. In that case, it was actually 300 millijoules. Okay, yeah.
You'd said it was phase lock. Phase lock to what?
A phase lock,
Crank angle?
yeah. Here, I think it's overshown here. The question, what is phase locked in this context? That has been performed in an engine, and that is relative to a crank angle, which has been fixed. The exposures were always for this crank angle. Yes?
So when we were doing this in Tomo, obviously we had, as you discussed, that post-processing is very tricky, and we were debating the value of doing a multi-plane dot target calibration.
Yeah.
What are your thoughts on how helpful that might be?
So the question is about the calibration you have to perform. And actually what I have done here is, oh voila, I have to go all that way through. Sorry. I think I had a view graph of the calibration plate, a commercial one. That is for stereoscopic PRV, but as well for tomographic PRV. So I think you need something like that as a starting point, because the question is you have to, or the issue is you have to match the cameras in top of each other, that you really exactly know which dot corresponds, let's say, to which pixel at one of these four cameras. So you have to do that as well in the tomographic PRV for different planes, and so it's really, of course, helpful if you then have a very precise translation stage where you can shift your calibration plate. And whenever you do stereoscopically this thing, you need these different planes. You need these different heights. Yeah, that's why you see the structure over here. And as I said, this is only a starting point. So at least one company came up with this so-called self-calibration and extended that to volume self-calibration. And the idea there is that based on this initial guess of this mapping, you take the particles themselves, let's say from the first exposure, to check whether these particles are at the corresponding positions on the cameras. And there might be still a small shift based on this calibration target, because you have information only at these dots, and in between you do an interpolation maybe with a third order or something like that. There still is room for, let's say, errors, and as well these dots are rather large. If you take the particles themselves, you can do better. And then the mismatch, the so-called disparity, should be in the order of, let's say, 0.1 pixel, yeah, such that you really have these cameras matched with the precision, or sorry, accuracy better than 0.1 pixels. Is that an answer?
Yeah.
Okay. So then let's go on with these examples. What you can gain from that, you see here the velocity magnitude, the average velocity magnitude in the tumble plane during the inlet of these combustion of this IC engine, where you have here the jet that is forming. You have two annular jets, and they merge in this plane where this has been measured, better seen in this projection. And then you have here the flow banded by the liner of the cylinder. You have here a stagnation zone where your flow that goes along the liner, along the piston, moving again upstream against the approaching flow, forming here the stagnation plane. And this gives you a nice, let's say, idea how this tumble motion is formed already during the intake. And that can be helpful in, as I said, understanding or get a better idea about the flow, and as well get all derivatives and all components of your vorticity and strain rate tensor. I think it's very important now as well to have a at least rough comparison between laser Doppler and particle image velocimetry. And so from my perspective, there are huge differences with respect to seeding. So for PAV, the advice is that you have something like 10 particles in your interrogation volume to get a reasonable estimate of the velocity. For that, if you have a fixed spatial resolution, let's say you're aiming for something like a millimeter resolution in each direction, you have a minimal seeding density. Going lower is not possible. And we have had this example of a extinguishing flame. When the seeding density affects your flow, then you have to do something about that. You, of course, want to be non-invasive, and that means you have to reduce the seeding density, and that comes then along with the fact that you need larger interrogation volumes. And that might be not what you're after. That's why laser Doppler velocimetry actually in this regard is better, because you can reduce the seeding density as you wish. You might need longer because you're just waiting for the particles crossing your probe volume, but the technique itself is not dependent on the seeding density. So that's a large difference. But it can, of course, take much longer than that you receive or monitor sufficient events to build up reliable statistics. The next is the calibration and the data post-processing. So in PAV, you rely on a cross-correlation algorithm, which takes some time. Of course, with better computer facilities these days, CPU times are maybe not an issue, but typically you take the data and then you do the post-processing. And that is not at the same time. And my advice would be here, take some data, do the post-processing and check whether your alignment, your parameters and so on are okay. And then go back and take the full set of data that you plan to build up your good statistics. Okay, another point is you have to do the calibration. We just discussed that with the calibration target. That brings you from the pixel to the millimeter scale, or from millimeter to pixel scale, and is really dependent on your way you do that. Do it thoroughly and it's okay, but do it as well with this self-calibration I mentioned briefly. If this is not done properly, you're inaccurate. Your results will be false. In LDV, if you buy a good instrument, and then it should be ready to be used, and you do not need any calibration as a user, because the size of the probe volume, for example, is well defined, such that as well as the angle between the two beams is well defined, that all these parameters are not freely chosen. And so they are fixed by the design of this instrument. And that's why it is, in that sense, more robust. Another benefit of LDV is that the post-processing is done online, such that you directly see during the measurements what your statistical quantities are doing, the mean, the PDF, for example, of these velocities you're measuring. So that is a clear benefit, but of course it's only a point-wise technique, and PAV is a field method. And then concerning or the results of that, if you somehow evaluate these measured variables, I would still say laser Doppler velocimetry is more reliable if you have interest in point data, but investigation of the neighborhood of one selected probe volume, for example, in terms of a spatial correlation, their LDV is really very, very cumbersome. It takes time, it's very expensive, and that's why PAV takes over more and more as well, because you get, for the same measurement time, so much more information that these benefits by LDV are really sometimes overcompensated by PAV, where you have access to these instantaneous velocity fields. And then from that as well, you get estimates of the gradients. Of course, these are apparent gradients because your spatial resolution might not be sufficient to resolve everything. Yeah? So that is as well something like a low-pass filter, and it can be wrong in areas where you have a very strong gradients. And that means as well, it could be helpful that you change your interrogation volume size in post-processing to see how sensitive your gradients are reacting on that. Okay, that is about the LDV story and the PRV story. Are there any questions? Yes?
I think in the slide 33 you mentioned that one of the stages of post-processing is Gaussian smoothing. If you use Gaussian smoothing, the fluctuation should flatten out, and if we are for instance interested in Reynolds shear stress, it should underestimate.
Yes.
Is there any better way to do post-processing to get rid of that noise without underestimating?
So the question is, if you use any kind of filtering in the post-processing, of course that harms the fluctuation level, which is as well reduced. The problem, if you don't do that, then you have, of course, higher fluctuation values, but you want to avoid, then it's, you get different results, of course, but they're then more strongly influenced by the noise. And the question is how to do that really reliably without taking, the idea is, of course, you would like to remove the noise and keep the information. And if they're overlapping, then it's not feasible to do it. And so I have no clear answer to that because we do not know about the noise characteristics to have a clear cutoff frequency. And so that is something you should vary your parameters, let's say in that way. That is maybe true for all of the post-processing in imaging diagnostics. You have a number of parameters that you can change in a certain sequence of the post-processing. And if you vary the parameter and your result is changing dramatically, strongly, you have a strong sensitivity, then you have to be very careful. If you have a parameter where the changes are not sensitively changing the result, then I would say you're fine. Yeah? And so that is something you should be aware of, you should report as well in your PhD thesis. Maybe it's more difficult in a short paper to bring that all in, but I think the answer, the most general answer I can give is this kind of sensitivity analysis. Okay. After that, after we have now seen how you can access the flow fields, as I said yesterday, the next step would be in flame diagnostics that you try to measure scalars. Scalars are temperatures and species concentrations. And so we start now here with temperatures and more precisely gas phase temperatures. And so within this chapter, I would like to show you what kind of possibilities we have. Before I start, all of these methods to be explained are based on spectroscopy. And that is something which is very different from the velocimetry, which was simply based on me-scattering of particles. So why is it so important to look at the temperature? Of course, you know, in combustion we convert chemically bound energy to thermal energy that can be then used for, be transformed in mechanical energy, for example. But if you refer back to what a combustion process is, it is in its backbone a process interlinking transport with chemical kinetics. And here temperature is of strong importance because the transport properties based on density, viscosity are temperature dependent, and the chemical kinetics depend, of course, as well due to the Arrhenius type characters on the temperature as well. And so because these processes take place as well at the same time scales, you have a strong interaction between transport and chemical kinetics, making combustion so difficult to understand and predict. Of course, you have as well other processes like evaporation phase change, for example, that is strongly dependent on the temperature. You have temperature gradients giving rise to heat transfer, where you have to know locally the temperatures, and emissions as well are strongly dependent on temperatures, local temperatures, such that it's one of the primary things in experimental combustion research to have good methods measuring this quantity. So it's a key quantity, as I said, because of chemical kinetics. It is influencing changing the gas density and the viscosity. In some of the model approaches in premixed combustion, for adiabatic conditions at least, the temperature can serve as well as progress variable. And overall, you can say, without knowing the temperature, you would not be able to access turbulence chemistry interactions. So you must somehow need to measure that. So ideally, you do this accurately without any systematic error. And ideally, you reduce your noise furthermost such that you're really precise. And you have to measure it locally. And locally is dependent, of course, on the flow, the flame itself, because you do not want to filter, again, in your probe volume, different areas of different temperatures. So ideally, you resolve the Batchelor scales. And so here we have now to distinguish what we're after. So if you want to measure the temperature in laminar flames and stationary conditions, then there is no temporal variation, but there might be large spatial variations. For example, over the flame front. Of course, for increasing pressures, this would get even steeper, and accordingly, you would have to need or apply a higher spatial resolution. So the requirements in time are none, as long as you're stationary. By experience, to make a laminar flame stationary is really difficult. You have to protect it from any movement in the lab, and so even there, very often, although you have a laminar flame, it might change its position. It flips back and forth, such that in reality, you still need a sensor which does have a certain time resolution, which is smaller or better than the fluctuation of your flame. In space, you have really, in laminar flames as well, requirement for high spatial resolution because of these steep rises in temperature in the flame zone where the heat is released, of course, depending on the pressure and fuel and so on. But ideally, resolve all these smaller scales, even in the flame front. In turbulent combustion, assuming statistically stationary, of course, you do have a large temporal variation in addition to the large spatial variation, such that in time and space, you ideally resolve the Batchelor times and length scales. Okay, so why not using intrusive sensors? Thermocouples and resistance thermometers are very well-known instruments, and for many applications, they are really good. However, for reactive flows, you have a number of disadvantages. One disadvantage is, especially at high temperatures, you have systematic errors because of heat conduction. Yeah, if you measure somewhere here, heat is transported, and that needs to be corrected for. These systems do radiate, and if you have passed a certain temperature, you need to correct for this radiation losses in a model. And there are different models on the market, and I cannot really tell you which one is the best, and they give differences. And the differences can be more than 100 K. So this is really a problem for flame temperatures. They impact the flow, as you can see. You have to stick them in, that's clear. And depending on the material and the flow itself, they might promote catalytic reactions. And thereby, they're heavily intrusive. Furthermore, they don't last very long. Even if you go for type S thermocouples and you go for, I don't know, methane air flame, stoichiometric, without too much heat losses, you have an adiabatic flame temperature, let's say, assume that, 2,200 Kelvin, then there is no thermocouple that will survive that. They are specified for something just below 2,000 K, and even then, they wouldn't last for very long, and they're expensive. They're large. Of course, you can try to produce thermocouples as thin below 100 microns, but there's no fun. They will not. They will last even a shorter time. And they have a certain response time. You can approximate them as a first order system with a certain time constant, and it is shown over here. If you have a, here the temperature, here's the time, sorry, that is in German. And if you would have a time step like, a temperature step like that, then your system would follow not directly because of the inertia, the thermal inertia, and this is a first order system behavior with a certain delay. And that means you have again a low pass filter characteristics, and high fluctuations of the temperature as in turbulent flames could not be followed. So that's why we really prefer methods based on spectroscopy and not rely on these intrusive sensors. So these kind of non-intrusive sensors, as I said, all of them based on spectroscopy, what follows, can be classified. First of all, you can think maybe use directly the thermal radiation of your flame. Yeah, why not? It is okay if you have particles, let's say soot particles, with known emissivity, then it can be used. But in gaseous flows, that will be not easily possible. Why not using chemoluminescence? Here you see our swirl burner, which was seeded, by the way, with too much seeding particles. This is not soot over here, what you see. This is the glowing of the seeding particles, magnesium oxide. This is heavily overseeded. It gives a nice picture, but you can see as well if you do it wrong, just a side note, you have changed your radiation properties of the flame strongly if you overseed the flow. However, what I would like to refer is to this bluish area over here. Anyone knowing what that is? Where's the color coming from? Chemoluminescence. And which molecule? CH. If you see it in this blue, it's CH. If it's in the UV, let's say 312 nanometer, it would be OH. If it's a reddish color, typically in the exhaust gas, that is water vapor. So why not using that? These compounds are electronically excited. They are not in equilibrium. And if they're not in equilibrium, there is no temperature defined. And so that cannot be used. That's why we have to do it differently. And you can classify the spectroscopic methods into those probing the Boltzmann distribution of quantum states, typically for rather small molecules. The next is you exploit temperature-dependent absorption or emission bands. In the end, that is, of course, as well linked to Boltzmann distributions to be explained. But these are rather large molecules where we do not have the full access of their quantum mechanical description. That's why I would like to distinguish them. Or the third class, you try to measure the density of certain probe volumes, and then you assume an equation of state like the ideal gas law, and then transfer the density to a temperature. So these techniques can be well suited for our purposes in thermometry in at least gaseous flames, but it's really important to note that there is not the single best method. It really depends on the purpose. It depends on your combustion system. And there's a clear disadvantage. In any case, it comes up with a high effort, and there is a need for expert knowledge. And of course, you need optical access, like in LDV and PIV as well. But because of that fact, the effort is high, and you need some knowledge about it, how to do it. That's why in the industry, at least in Germany, it's not so well established. So there are only a few companies, for example, engine manufacturers, using these techniques. And so I would like to go a bit further into this classification. If you use the Boltzmann distribution, that's a very nice way to measure temperatures. So who knows about the Boltzmann distribution in this room? Okay, that is maybe half of them. For the others, I'll try to make a short explanation. The Boltzmann distribution, coming from the statistical physics, is a great equation. Why? It links a thermodynamic state variable, the absolute temperature, over quantum mechanical properties that can be deduced in the end from the Schrödinger equation, having here the energy values of certain eigenstates of your molecule and the Boltzmann and the degeneracy factor. The temperature is linked over these quantities to so-called Boltzmann fraction, which gives you the number of molecules that are in a specific energy state I given here. Okay, and thereby, if you're able to measure this Boltzmann fraction, so measure the number density of molecules that are in this specific energy state, then you're able to directly deduce the temperature. Of course, you assume thermodynamic equilibrium. If this is given, if you do these measurements with the knowledge about this factor over here, I will specify that after the break, and with the knowledge that we have from quantum mechanics about the energy levels, you have, without any calibration, a direct access to the absolute temperature. And that is very, very charming. Of course, we have to discuss how to do that, which techniques can be used, and which levels are most suited for that. The next class was about the temperature-dependent absorption or emission. So the idea shown here for the emission, for in this case it's toluene, a tracer molecule, we go into more detail into that is typically seeded to the flow. What you see here, that after this is normalized, however, if you excite these molecule, then you see for increasing temperature that the emission band, here's the wavelengths, here the normalized fluorescence, that the emission is shifted further to the red. And this information can be decoded after calibration, I have to say, with the calibration to temperature. Or the third is that you, as I said, use the density, meaning the number of all molecules independent of their distribution to different energy levels in a certain probe volume, in combination with an equation of state, here the ideal gas law, and then get a temperature with a known pressure with the Boltzmann constant, and here this number density. You can access as well the temperature. But this needs as well a calibration. So the method number 2 and 3 needs calibration, and if you trace it back to the Boltzmann distribution, you can do it without any calibration. So this actually is, in that sense, at least to me, the preferred method, if applicable. And so just a few words. We will, after the break, restrict ourselves to diatomic molecules. So these molecules, for example, H2, O2, NO, and things like that, these are atoms that are covalently bounded. And what we need here only is the fact that we have different internal degrees of freedom. Okay, so each molecule, of course, has 3 degrees of freedom with respect to translation. It can be going in each of the 3 directions. But you have as well internal degrees of freedom, and those are needed for the discussion in the following. You have the possibility to electronically excite these molecules, meaning that the outer electrons, and we only refer to them here, the outest molecule electron, which is called the valence electron, can go from a ground state to excited states, first, second, and so on, and is classified or described by its quantum numbers. No time to go into detail here. There is another internal degree of freedom. These, for a given electronic state of the valence electron, this molecule might vibrate. So meaning that the nuclei, for example, here for the hydrogen molecule, they change the distance to each other with time, and they can rotate. Why are there only, I think it's clear that you have only 1 degree of freedom in terms of a diatomic molecule, only 1 degree of freedom in terms of vibration. That's, I think, clear. Why do you have only 2 degrees of rotation? Any idea? So if this is the molecule, they're in line, yes, and we assume that the masses are point masses and are primarily in the nuclei, and that means you have in this direction no inertia, and that means you have no rotation. So such a molecule can rotate only in this direction and this direction. And that means we have here these 2 degrees of freedom in rotation. And so we will go through them and find out then after the break which degrees of freedom are most suited for thermometry in the gas phase. With that, we have now 10 minutes to 10. I think we should have a break of 15 minutes, and we restart in 10:05. Thank you very much.